Good evening to all. Today we are starting with fluid machinery subject. Actually, fluid machinery subject is with respect to the various application of fluid mechanics. So in fluid mechanics, we had discussed a lot about various theories, viscosity, density, Bernoulli's theorem, etc. So here we are dealing with the uh, application side of the fluid moment. So the moment of fluid is utilized for making energy. So for extracting energy from the fluid, we need certain devices such as turbines, pumps, etc. So these devices are used for extracting energy from the fluid. So as an introduction, we need to study the behavior of the impeller. So impeller absorbs the fluid's energy. So let us start with the impact of a jet. So here we are utilizing a jet of fluid. Jet of fluid means the fluid delivering from a stream of fluid delivering from a pipe is known as jet of fluid. So this jet of fluid is allowed to strike on an impeller. So first of all, we are discussing about the impact of jet on a fixed vertical flat plate. So this is the flat plate we are using. So in this flat plate, we are injecting a stream of fluid. So a stream of fluid issuing from the nozzle is known as jet of fluid. So for that, a nozzle is this portion is the nozzle. A nozzle is fitted to a pipe, and through this nozzle, a stream of fluid is issuing. So the velocity of fluid is V, and A is the area of the pipe, area of the stream. That means if a D is the this is the stream, so if small d is the diameter of the stream, so area A is equal to pi by 4 d square. So area A is equal to pi by 4 d square. This velocity, so velocity with which the fluid is issuing from the nozzle is V, and this fluid is striking a vertical plate which is fixed one. So after striking the vertical plate, the fluid moves in this direction, upward and downward direction. So there is no fluid in the x direction after striking the plate. Okay. So so consider a jet of water coming out from the nozzle strikes a vertical fixed plate. So let V the velocity of the jet. V is the velocity of the jet. A is the area of cross section of the jet. So we need to find the force exerted by the jet on the plate. So the jet after striking the plate will move along the plate. That is, and the jet will deflect it through a 90 degree. So the jet is deflecting through a 90 degree. It is striking here and deflecting at a 90 degree angle. Hence, the component of velocity of jet in the direction of jet after striking will be 0. So, the component of velocity of jet component after striking the plate in the direction of jet. That means the direction of jet there is no component of velocity after striking the plate. So, in order to find force exerted by the jet on the plate in x direction, f of x is equal to f of x is the force exerted by the jet in the x direction. So f of x is equal to rate of change of momentum in x direction. Rate of change of momentum means what? Initial momentum minus final momentum. So what exactly is momentum? Momentum is m into mass into velocity is momentum divided by time and gives the rate of change of momentum, that is initial momentum minus final momentum divided by time gives the rate of change of momentum, which is the force exerted by the fluid on the vertical plate. So m into v is the momentum, so mass into initial velocity is the initial momentum, mass into final velocity is final momentum divided by time. So mass is the common term, so we are taking mass outside and time is also taking outside. So what exactly is mass of fluid striking the plate? It is density into area density into area, mass into v velocity. So actually mass is density into volume, so here we are taking it as velocity, which is the displacement by time. So a into l by t it is getting, so mass per time we are getting here, it is mass by t is equal to rho a v. So rho a v is the mass, initial velocity with which jet strikes the plate is v, and final velocity with which jet strikes the plate is 0. Okay, so combining these two will give rho a v square. Rho a v square is the force with which jet strikes the plate when the plate is placed vertically. So what will be the work done? Work done in this case, so work done is equal to force into f of x, force in the x direction, into displacement is the work done. Displacement is the work done. So here the displacement is 0, so f of x into 0 displacement, there is no displacement since the vertical plate is stationary, since the force exerted by the jet does not move the vertical plate. So the vertical plate is not moving, so that means the plate has no displacement. So since displacement is 0, therefore work done is equal to 0. So this is the equation for the force exerted by the jet on a vertical plate when plate is stationary. Okay. So force equation is rho a v square and work done is 0 in this case. Okay. So next portion is earlier we discussed about a vertical plate, but here we are placing the plate at an angle with the jet. So we are placing a plate, an inclined plate at an angle theta with the jet of fluid. So now we are going to discuss about the force exerted by a jet on a flat fixed inclined plate. Okay, so we are discussing about an inclined plate which is stationary. This is fixed here, so it will not move, and the jet of fluid is striking the plate, and the plate and the jet of fluid makes an angle of theta. So theta is the angle. So this so the jet of fluid is striking at an angle theta. So component of velocity perpendicular to the plate. So component of velocity perpendicular to the plate, this is theta. So this angle will be 90 degree. So this angle will be 90 minus theta. So this portion v sine theta. Velocity component normal to the plate is v sine theta. So f of n, force exerted by the jet normal to the plate. Force exerted by the jet normal to the plate is this is equal to force exerted by the jet normal to the plate is f of n. So mass into, as we said earlier, so mass per second into initial velocity minus final velocity. So mass per second is rho a v, and the initial velocity with which jet strikes the plate is v sine theta. V sine theta. That means the normal component of velocity to the flat plate. So V sine theta. There is no normal component after striking the plate. There is no normal component after striking the plate. So final velocity is 0. Therefore, the normal component of force acting on the plate is rho a v square sine theta. Rho a v square sine theta. So we are going to find the x component, and we are going to find the x component, which is f of x, and also the y component f of y. So f of x is equal to so from this diagram, this is normal component, this is vertical component, and this is horizontal component. So f of x is equal to f of n cos theta. F of n cos theta, cos 90 minus theta. Sorry, it is not cos theta. Here it is 90 minus theta. So f of n into cos 90 minus theta gives f of n sine theta. So cos 90 minus theta is f of n sine theta. So we know that f of n is equal to, and then f of n is equal to rho a v square sine theta. So f of n sine theta is equal to f of n sine theta is equal to f of x and sine theta is equal to rho a v square sine theta into sine theta. So rho a v square sine square theta. Okay, so the x component is equal to rho a v square sine square theta, and y component similarly f of n sine theta sine 90 minus theta gives y component. Therefore f of n cos theta. So rho a v square sine theta into f of n is rho a v square sine theta into cos theta gives rho a v square sine theta cos theta. So x component is rho a v square sine square theta, and y component is rho a v square sine theta cos theta. So next we are going to discuss about the force exerted by the jet on a stationary curved plate. So here we are, instead of a flat plate, we are taking a stationary curved plate and curved vane, and the vane angle is theta. Theta is the vane angle. Okay, so here the jet strikes at the center of the plate. So the jet is striking at the center of the plate. V is the velocity of the jet. A is the area of the jet. D is the diameter of the jet. Okay. said earlier, the force exerted by the jet is equal to on the plate, and this curved plate is also stationary. So we need to find the force exerted by the jet on the plate. So mass per second into that means initial momentum minus final momentum, that is taken as mass per second into initial velocity minus final velocity. So initial velocity with which, so I will write it here. Initial velocity is equal to v. Final velocity, final velocity in x direction. Final velocity in x direction is equal to, so final velocity after striking the plate, the jet moves back at an angle theta, and final velocity in the x direction is equal to v cos theta. If it is leaving the plate at a velocity v, same velocity with which just striking the plate, leaving with the same velocity v, but making an angle theta. So in the x direction it is v cos theta. So initial velocity is v and final velocity is equal to v cos theta. So that means x component of v. So the equation becomes rho a v into v minus v cos theta. Why there is a minus sign? Because it is moving in the opposite direction. So here it is negative. The jet is after striking the plate, it is moving in the opposite direction. So it is taken as a negative. So v minus v cos theta. We are taking it as v minus v cos theta. So the equation becomes f of x is equal to, so f of x is equal to rho a v into v minus v cos theta. So the equation becomes rho a v square into 1 plus cos theta. So this is the equation. So in the y component, so there is a component of velocity in the y direction. So y direction, the component of velocity is v sine theta. X direction v cos theta, and y direction v sine theta. So mass per second, y direction, force exerted by the jet in the y direction is equal to mass per second to initial velocity. So initial velocity in y direction, there is no initial velocity in the y direction. Okay, so initial velocity in the y direction is 0, and final velocity in the y direction is v sine theta. So the equation becomes f of y is equal to minus rho a v square sine theta is the equation. In this condition also, this case also, the work done equals 0, because there is no displacement in the direction of a jet, and there is no displacement of the plate in the direction of a jet, therefore the work done is 0. About the jet strikes at one end of the plate, and the plate is symmetric. That means what we are considering a curved plate, and which is a symmetric one. Symmetric one means the jet or the blade angle at the inlet and blade angle at the outlet are same. That means theta is theta at the outlet and theta is at the inlet. So jet is striking from the one end of the vane, that is the pipe, and the nozzle is fitted at the one end of the vane, and the jet of water leaving at the other end. So here also we need to find the force exerted by the jet in the x direction, and also we need to find force exerted by the jet in the y direction. So y and x direction we need to find. So the velocity with which jet strikes the plate is v, and it makes an angle theta. Since the inlet angle of the vane is theta, the jet also makes an angle theta and with the inlet. So theta is the inlet angle and v is the inlet velocity. So x component of inlet velocity becomes its v's x component becomes v cos theta and y component becomes v sin theta. And after striking the vane, it leaves the plate at a similar angle, that is theta itself. The jet is leaving the vane and it is making at an angle theta, and the x component at the outlet is v cos theta and y component is v sin theta. So we are finding first we are finding the x component, force exerted by the jet in the x direction. So initial velocity with which jet strikes the plate is v cos theta, and the final velocity with which jet leaves the plate is v cos theta itself. So the mass per second is similar, rho a into v, rho a v into initial velocity v cos theta minus minus, since the jet is leaving at in the opposite direction, and the opposite direction of the jet at inlet, so we are considering another minus, so minus v cos theta. So the term becomes rho a v square, as we are taking the v out, the term becomes rho a v square cos theta is the common term, also the 1 plus 1. Okay, so the equation becomes 2 into rho a v square cos theta. Next we are finding and the y component of the jet force, y component of the jet force. So mass per second into initial velocity minus final velocity. So initial velocity with the jet strikes the plate is v sin theta, and final velocity with the jet leaves the plate is v sin theta itself. Okay, so f of y becomes rho a v into v sin theta minus v sin theta, since both at inlet and outlet the direction of jet is in the same direction, there is no additional negative sign, positive itself. So the y component becomes 0, v sin theta minus v sin theta is 0. So what will happen if the curved plate is unsymmetrical? That means at inlet the velocity with which just strikes the plate is v and it makes an angle theta at the inlet, and it makes an angle phi. That means the inlet vane angle and the outlet vane angle are different. So we are considering the jet strikes at one end of the plate and the plate is unsymmetrical. So unsymmetrical means inlet angle is different from the outlet angle. So the velocity component is velocity with which jet strikes the plate is v. So the y component becomes v sin theta and the x component becomes v cos theta. Theta is the angle with which jet strikes the plate and it is leaving at an angle phi. It is leaving at an angle phi. So x component of the velocity becomes v cos phi and the y components becomes v sin phi. So what will be the force components in x and y direction? So similarly, as we stated earlier, the mass per second into initial velocity minus final velocity. Rho av is the mass per second. V cos theta is the initial velocity with which just strikes the plate. Minus term will be there, since the in x direction it is leaving the plate at in the opposite direction. So minus term will come, v cos phi. So rho a v square into cos theta plus cos phi is the equation, and f of x is equal to rho a v square cos theta plus cos phi. F of y becomes mass per second into initial velocity with which jet strikes the plate minus final velocity. Initial velocity v sin theta, but final velocity is v sin phi. So rho a v square sin theta minus sin phi. So f of y is equal to rho a v square sin theta minus sin phi gives the force in the y direction. So that's all for now.